Chapter 8, Section 4 is going to cover Earth's layered structure. Earth's layers are defined by their composition. Earth's interior consists of three major zones defined by their chemical composition: the crust, the mantle, and the core. The crust itself is a thin, rocky outer layer divided into oceanic and continental crust. It can exceed 70 kilometers in mountainous regions. Here we can see how those seismic waves we talked about in the last section can travel through the Earth based off of their composition. So those P and S waves will travel differently through solids than they will through liquids. And then that will also cause a rebound with that solid inner core if it passes through that. So the continental crust itself is the upper crust composing of granitic rocks, and the lower crust is more like a basalt. The average density is about 2.7 grams per centimeter cubed. The continental crust is up to 4 billion years old. It can average 8 all the way up to 40 kilometers thick, but in some regions it can exceed 70. The oceanic crust has a basaltic composition, and it varies in thickness. Roughly on average it's about 7 kilometers thick, and its density is about 3 grams per centimeter cubed, so it's more dense. But it's also much younger. The oceanic crust is 180 million years or less than that of the continental crust. The mantle is a solid rocky shell that extends to a depth of 2,890 kilometers. Its composition in the uppermost mantle is the igneous rock peridotite. As you go deeper, it can change. Below that lies the core. This is going to be a sphere with a radius of 3,486 kilometers. It's composed of an iron-nickel alloy. Its average density is nearly 11 grams per centimeter cubed, so that's extremely dense. If we look at the physical properties, we can define layers a little different. The lithosphere is made up of the crust and the uppermost mantle, up to about 100 kilometers thick. It's going to be very cool, it's rigid, and it's solid. The asthenosphere, on the other hand, is soft and comparatively weak, and it lies beneath the lithosphere. The upper mantle makes up the asthenosphere, all the way down to about 660 kilometers, and this soft, weak layer is very easily deformed. So here you can see the asthenosphere and the lithosphere. The lithosphere is that rocky crust layer, and the asthenosphere is that upper mantle. The lower mantle, from 660 to 2,900 kilometers, is a more rigid layer that envelopes the core. The rocks here are very hot, and they're capable of a gradual flow. The outer core is a liquid layer. It's 2,270 kilometers thick. There's a convective flow of metallic iron within it, and that's what generates Earth's magnetic field. The inner core, the very, very inside, behaves like a solid sphere, and it has a radius of 1,260 kilometers. It's also made up of that iron-nickel alloy. During the 20th century, studies of the paths of the P and S waves through Earth helped scientists identify the boundaries of Earth's layers and determine that the outer core must be liquid. The boundary that separates the crust from the underlying mantle is what we call the MOHO. Here we see another picture of the earthquake epicenter and those P and S waves traveling. You can see how they travel through solid, but as soon as they hit that liquid, they change path. Think of if you've ever put a pencil in a glass of water, how that looks, that refraction. So light is made up of waves. So light travels in waves. So if this was light and it was traveling through a solid and hit liquid, it would change. Just like when we look at the pencil in the glass of water, the light travels through air and then it hits the liquid and it refracts differently. That MOHO, we're going to see the velocity of seismic waves increase abruptly below that 50-kilometer point. We also have this shadow zone, which is just the absence of P waves from about 105 to 140 degrees around the globe from the earthquake. It can be explained if Earth contains a core composed of materials unlike the overlying mantle, so we have alternating layers. Now keep in mind this also, it only works if the Earth is a sphere. It's not flat. To determine the composition of Earth's layers, scientists studied seismic data. They looked at rock samples from both the crust and the mantle. They also looked at meteorites, and they did high-pressure experiments on Earth's materials. They were checking to see how did these waves travel through different types of materials. The crust, the early seismic data, drilling technology indicated that continental crust is mostly made of lighter granitic rocks. The mantle composition is more speculative because we can't visit there, we can't go there. What we know of the mantle comes from the lava that reaches Earth's surface, and it's very limited in our knowledge of what the mantle is actually like. The core, obviously, we don't know, but based off of the data that we've generated, the Earth's core is thought to be that dense iron and nickel. It's very similar to the metallic meteorites that they've collected. The surrounding mantle is believed to be composed of rocks that are very similar to stony meteorites. So if we could cut the Earth open and look at it, this is essentially what we're looking at, this anatomy of the Earth. When you made your Earth's layers foldable, you were looking at a piece of the pie slice of this image right here with all the information. And that is layers of the Earth and how earthquakes are made.